Welcome to the New York Combinatorics Seminar. Our speaker today is Calum Buchanan, and he will speak on saturation numbers. Calum, the floor is yours. Thank you.
Hey, thank you very much, and thank you for inviting me. Yes, so I'm Calum Buchanan. I'm a graduate student getting a PhD at University of Vermont under the advising of Puck Rombach. And this is a project that we've worked on together, or it's work based on a project that we've done together. And the title of this talk is A Lower Bound on Saturation Numbers and Its Effectiveness on Certain Trees. So as I was just saying before the recording started, I much prefer giving chalk talks, so I'm going to try and make this feel a bit like a chalk talk as we go. On the other hand, if I don't have a blackboard, I might just finish my talk here. So thank you very much for having me, and no, I will proceed as follows. So the outline of the talk is like this. I'm going to first give a little history on extremal graph theory and extremal combinatorics. More of a history of extremal graph theory and some preliminaries on this function that we call the saturation number. I will then talk about some general lower bounds that we have on the saturation number and proceed to talk about some strengthenings that we can get of these lower bounds when the graph is triangle free. And I'll finish by talking about saturation numbers of some trees, in particular double stars and a caterpillar named Shorty. So without further ado, so I'll talk a little bit about maybe just how I think about extremal combinatorics. I've seen a couple of different definitions given, and to be honest, I'm not fully satisfied with any of them. But here I'll give two. So sometimes I hear this as extremal combinatorics is the study of optimal sizes of combinatorial objects which are subject to some constraints. Optimal sizes of combinatorial objects subject to some constraints. And I do think that this is perhaps a broad enough definition to be encompassing. But optimal sizes always bothered me a little bit. We're not always looking for a maximum. We're not always looking for a minimum. There are lots of, I think, extremal questions, which are more along the lines of this second definition, which is how I will kind of think about things today and relates quite well, I think, to the study of saturation numbers. One can think of extremal combinatorics or I think sometimes of it as being how do local properties and global properties of combinatorial objects play together? How do local and global properties of combinatorial objects play together? And so perhaps I will proceed by means of example. So I like graph theory. Graphs are my favorite combinatorial objects. And in particular, I'm going to talk about finite simple graphs. So today, finite simple graphs. And what I mean by finite is that it has a finite number of vertices. And what I mean by simple is that we don't have any loops, so an edge connecting a vertex to itself, and we don't have any multiple edges. So a pair of vertices can be joined by at most one edge. So one of the first questions, perhaps the first question in extremal graph theory, was posed by Mantell in 1907. So Mantell asked, what is the maximum number of edges that a graph with a given number of vertices, which does not contain a triangle, can have? So Mantell, 1907, what is max number of edges in an n-vertex graph with no triangle? So that is three vertices, which are all connected by edges. And although it was a student of Mantell's who answered this question, this is commonly known as Mantell's theorem. The answer is about n squared over 4. So how do we go about doing this? So I'll say approximately n squared over 4. So if we start with some set of vertices, I don't know, let's do 5 vertices. Certainly, at the moment, this graph contains no triangles. It has no edges to be in a triangle. And one can start just sort of adding edges one by one until you get stuck somewhere. So I could start by adding in some edges like this. And if I add in all of the edges from this one vertex and make a star, I'm now stuck, right? If I add in any extra edge, I make a triangle. And this is true of any star, a star on any number of vertices. You can't add any extra edges without creating a triangle. But you might notice that a star is a tree, and thus it has a number of edges which is linear. It's n minus 1 edges, whereas the answer here is on the order of n squared. And so we can actually do better if we don't start by making a star, and we connect vertices in this way. So now we can get 6 edges instead of 4 edges. Still, we contain no triangle. And it is maximal. We haven't proven here, this, to be honest, this is the maximum graph, but I won't prove that right now. Yeah. So for n equals 5, the answer to Mantell's question is in fact 6. Okay. So Mantell's question from 1907 was generalized into like what is now kind of the cornerstone of extremal graph theory, known as Turon's theorem. So Turon in the 40s, 40s, asked and determined the maximum number of edges in an n-vertex graph with a given clique number. Omega. So the clique number here is the maximum size, maximum cardinality. A clique. So not containing a triangle means that you must have clique number 2. If you have clique number 3, then that means that you contain some triangle. And what Turon showed was that a graph which is now known as the Turon graph, obtained by partitioning your n vertices into omega different parts of as close to equal size as possible. and then taking the complete multipartite graph on that set of vertices. Uniquely contain, this is the n-vertex graph, which uniquely contains the maximum number of edges out of all n-vertex graphs with clique number omega. So right, this is omega different partite sets. Okay. Now, in 1949, in a paper that I only recently found and actually isn't cited nearly as much as I think it should be in the saturation literature. In 1949, Zykov, perhaps unknowingly of Taran's theorem, I do not know, reproved this result in slightly different terminology. So Zykov in 1949 studied, so he studied saturated graphs. I'm going to put this in quotes because the type of what I'm going to call saturation later in the talk is a more general version of what Zykov studies. So actually, maybe I will call these omega saturated graphs. Okay, that way we can all be clear that when I switch my terminology. Studies omega saturated graphs. So these are graphs which are maximal with respect to having clique number omega. They don't necessarily have the maximum number of edges, but we cannot add any more edges without increasing the clique number. Cannot add any edges without increasing the clique number. And this is sort of the origins of the study of saturation, because now and it's part of why it goes back to why I prefer the second definition that I gave, even though sometimes honestly this second definition of extremal combinatorics runs into problems. I will be there are problems which I am sure are extremal problems, which aren't necessarily about local and global interactions. So I will make a note there that I'm aware that like one can ask questions about forbidding Hamiltonian cycles, for instance, which are certainly a global property, whereas just looking for triangles is a local property. But like I say, for the purposes of this talk, I'm going to use that definition. And like I say, so what I like about this is that we're no longer looking for a maximum number of edges necessarily. We're interested in the structure of these graphs where we can't add any extra edges without increasing the clique number. So then in about 15 years later, in 64, Erdős, Hajnal, and Moon first addressed what is known as the saturation number. Erdős, Hajnal, and Moon. 64 determine the minimum size of an omega saturated graph. And so firstly, to ask for the minimum size of such a graph now makes sense. When we just ask about being triangle free, for instance, it's not very interesting to ask for the minimum number of edges in a graph which is triangle free, because the graph with no edges has no triangles. So the natural question in that respect was to ask for the maximum number. But once we introduce this idea of saturation, it makes sense to ask for the minimum number of edges in a saturated graph. Because of course, unless you are a graph consisting of a single edge. You know, unless it's the clique has size 2, the empty graph won't be saturated for anything. Right. Okay. And so what Erdős, Heinel, and Moon discovered is that the graphs which minimize the number of edges over omega saturated graphs look like Turon graphs. It's just that rather than having partite sets of balanced cardinality, you make them as unbalanced as possible. So now we're going to make omega minus one partite sets of cardinality 1, and then a big old independent set of cardinality. So I'll do an independent set by a complete complement of the complete graph of cardinality n minus omega plus 1. And we join all of the edges in this all of the parts in this multi-partite graph. So certainly this graph has clique number omega. You can take one vertex from the independent set and the omega minus 1 singletons and obtain a clique with cardinality omega. And if you add any edge inside of this independent set, suddenly you create a clique of size 1 larger. Okay. So there's our brief history. Oh, and I've taken a good few minutes giving you the brief history. So let's move on to what's the subject here. So we're going to generalize this notion of omega saturation, and in fact, it has been generalized since the 80s to H saturation. So now we will let H or let's let G and H be graphs. We'll say that G is H free if H is not contained in G as a subgraph. Doesn't have to be induced, just no subgraph of G. No subgraph of G is isomorphic to H. So let's take H to be something other than a clique this time. So maybe H will be this little path of length 3. If we take G to be well, let's start off with say six vertices. Currently G is H free. We can begin adding edges. We can begin adding edges to G and remain H free. So there I've added an edge. There I've added an edge and I'm still H free. There I've added an edge and I'm still H free. But now that I get to my matching, if I add any other edge, I will create a path of length 3. So I call such a graph H saturated. So G is H saturated if 1, G is H free, and 2, G plus XY does contain a copy of H for all non-edges of our graph. G. So in other words, it's H saturated if it is maximally H free.
Quick question.
Yes.
So by H free is induced subgraph, right? Not having
No.
induced subgraph. Is it minor?
No, I'm not talking about no induced subgraphs. I'm talking about plain old subgraphs.
Oh, okay. So it's not so H, it's not, doesn't mean that it doesn't have a minor and also not induced subgraph. So it's just a plain subgraph. Okay.
Just a plain subgraph.
All right. Thank
So,
you.
yes, it certainly, if it's H-free, then it certainly doesn't contain any induced copies of H, but just the fact that it doesn't contain an induced copy of H, it might, it might not be H-free, right? Yes. Not necessarily induced. Okay. And the saturation number. The most important definition for this talk. Oh, I'm not seeing my screen move, but hopefully it will catch up with me. The saturation number is the minimum number of edges in an H-saturated graph on n vertices. So the saturation number is a function of both a positive integer n and a graph H. And it is the minimum number of edges in an n-vertex H-saturated graph G. Right. So brief history of the saturation number. Casoni and Tusa in the 80s determined a general upper bound. So Casoni, Tusa in the 80s. So they determined that the saturation number is linear, which is quite interesting because the extremal number, the maximum number of edges in a graph which is H-free can certainly be quadratic, as we've seen from Mantel's theorem. But what they show is that there are no graphs for which the saturation number is more than linear. And they do this by construction. Upper bounds come from constructions, and they find a general construction, which gives a linear upper bound. It was a long time until anybody has found a general lower bound for the saturation number, which is not quite trivial. Let me give you a relatively simple lower bound before I tell you about Cameron and Pouleos. So a relatively simple lower bound. I imagine while Cameron and Puleo did not state this outright and they phrased their bound quite differently, I imagine that they did notice this a few years ago when they found their bound. So for each edge UV in our graph H, which is the graph that we are forbidding.
Sorry, is this
yeah?
edge an arbitrary edge or just the edge of the three edges you mentioned?
This edge UV, right, that I'm
so
about.
this edge, is this edge an arbitrary graph or the edge you mentioned before?
Yes. Oh, so do you mean so in the definition of H saturated, it has to be true for adding any arbitrary edge that you create a copy of H.
Okay, so here edge is an arbitrary graph, not any. So for arbitrary graph, the upper bound is linear.
Right. For an arbitrary graph H,
okay,
Casoni and Tusa construct an upper bound, which is a graph G, which is H saturated and has a linear number of edges.
Okay, thank you.
Yes. And there is some tricky stuff going on because we are considering yet two graphs. On the one hand, we have the graph H, and there's something special about this graph H, which is going to tell us about the graphs G, which are H saturated. So what I'm going to do is define a weight function. Actually, this is the theme of the talk today, is defining a weight function on the edge set of our forbidden graph H, which will tell us a bit about the average degree of an H saturated graph. And the average degree of an H saturated graph will tell us about its size. So for each edge UV in our graph H, we'll let I'm going to call the weight function weight 0 of UV be the maximum degree of an endpoint minus 1. The motivation for this definition is that if now we take our graph G, if G is H saturated, then what happens if we add in a non-edge xy in G? That non-edge now must be contained in some copy of H, which means that at least one of X or Y has to have the correct degree to be in a copy of H. In particular, if this edge is going to play the role of an edge UV in H, then at least one of X or Y in G must have degree weight 0 of UV. So an observation here is that if G is H saturated, then the set of vertices with degree strictly less than the minimum value of weight 0 over every edge over the edge set of H is a clique. We cannot have two non-adjacent vertices with too low of a degree to even be in a copy of H to begin with. And so what this tells us is that, well, this clique must be small. It can't have cardinality bigger than the minimum value of this weight 0 function. And so all of the rest of the vertices in the graph must have degree at least this minimum value, which I'm going to call K0 for now. And so what this tells us is that the saturation number for any graph H is always bigger than or equal to K0 times n over 2 minus C, where C is some small constant. And this is basically like, this is the average degree, approximately. So thanks to the handshake lemma, I'm going to say a lot of things in this talk that are phrased in terms of average degree instead of being phrased in terms of number of edges. But the average degree of an H-saturated graph cannot be much smaller than the minimum value attained by this weight 0 function. So Cameron and Puleo's bound from 2022. Puleo, 2022. They show that the saturation number, the average degree of an H-saturated graph cannot be much smaller than the minimum value over the edges of H of weight 0 of UV plus the number of common neighbors that U and V have together. N over 2 minus C. Sorry, let me put this so that it's like... And this is actually a really nice lower bound for graphs with lots of triangles for graphs. So it's tight for threshold graphs. Threshold graphs are graphs obtained from a single vertex by adding dominating vertices or isolated vertices iteratively. So all I'll really say about Cameron and Puleo's bound is it handles triangles very well, but for a triangle-free graph, it reduces to this sort of trivial bound, which isn't tight for lots of graphs. So let's go through some examples. So again, if our graph H is this path of length 3, it's triangle free, so we don't have to worry about the common neighbors. Actually, all of the graphs I'm going to talk about for the rest of today are triangle free, so let's do that. If it Cameron and Puleo's, the value of weight 0 here is 1, 1, and 1, because the maximum degree of an endpoint is 2, and we subtract 1, we get 1. And so what this tells us is that the average degree GH saturated implies the average degree D of G is greater than or equal to 1 on average, approximately. But a matching has average degree 1. And it works. We already saw that earlier in the talk. So that's lovely. On the other hand, if I do a path which is 1 longer than length 3, length 4, I still have weight values of 1 on every edge. But a matching is the only graph with average degree 1. And it certainly isn't saturated for a path of length 4. So not good enough. Now, I will note that Casogni-Tusa, in that same paper where they showed the linear upper bound, they solved the saturation problem for paths. So this specific example is solved. But I think that their construction for paths is a more general construction than they realized, I think. And I'm currently working on a follow-up project that would show exactly that. So let's look at one more graph related to the path of length 3 for which their bound isn't good enough. The chair. Here's a reclining chair. Here we have weight functions of 1, 2, 2, and 2 for weight 0. But when we minimize, we still get this, just the edge with weight 1. And so we still get a matching, but of course that's not good enough. So the question is, what can we do to make it good enough? Right? If we join two non-adjacent vertices, which each have degree 1, sort of the problem that we're seeing is that, well, we join this edge and it could play the role of this weight 1 edge. Except for that, once we take the neighboring edge, this one, we're supposed to get to a vertex that has degree 3. And yet we've gotten to a vertex which has degree 1. So that's a problem. So what I'd like to do is define a second weight function. A second weight function weight 1 of UV, so on the edges of H, which is going to be the maximum over the union of the neighborhoods of U and V, minus U and V themselves. I like to think of this as the neighborhood of the edge, UV, in case I write this again. It's like, it's all of the vertices which are adjacent to one of the endpoints, but not the other endpoint itself. And we're going to take the maximum degree of a neighbor of U or V. And now, what we observe is that not only is the set of vertices which, without degree k0, form a small clique, but also the set of vertices which don't have a neighbor of degree at least the minimum value of weight 1 should also form a small clique. Right? If k1 is equal to the minimum value over all edges in H of weight 1 of UV, and if GH saturated, then the set of vertices, the vertices in G without a neighbor of degree K1 form a clique. And this clique must also be small, because if it gets too big, then the vertices in that clique would then have a neighbor of sufficient degree to break this condition. So we now have these two small cliques. So what this tells us is that apart from two small cliques, we have that all vertices have degree k0 and have a neighbor of degree k1. So for a little warm-up, I know I should really start moving along here, so maybe I won't give you the warm-up. We can ask now, what is the minimum average degree of a graph which has a given minimum degree and every vertex has a neighbor of another given degree? What is the minimum average degree of G with min degree delta and every vertex with a neighbor of degree k? This was going to be my one proof of the talk, but I'm going to skip that one proof. The answer is just a little bit bigger than delta. It's not quite up at delta plus 1, but the answer is delta plus k minus delta divided by k. And this is obtained by a graph that looks like this. So we have a set of what I'm going to call the large set, denoted by L, and the small set, denoted by S. And we, well, every vertex in L, every large vertex also has to have a large neighbor, because every vertex has a neighbor of degree k. And then it can have all of the rest of its neighbors in the small set. And this minimizes the average degree. You get kind of a maximum ratio of small vertices to large vertices. Okay. So if I go back to my path example now, let me maybe just do a similar one. So for the path of length 4, we have weight 0 values of 1, and we get weight 1 values of 2. every edge has a neighbor of degree 2. And so this does push up the lower bound a little bit. Very good. But it's still not quite good enough. Because in this graph, if I look at the one edge, the edge with weight 0 equal to 1, it has a neighbor of degree 3. But this edge with weight 0 equal to 2 has all of its neighbors having degree 1. So now when I minimize the weight 1 function, I actually get something less than the minimum degree that I'm going for. That's not good enough now. What I really want to do is pay attention to this edge. So what I'm going to do, instead of minimizing weight 1 over all of the edges in the graph, I'm going to minimize weight 1 over all of the edges which minimize weight 0. And from this, we will obtain our bound. I can finally state what the lower bound is and tell you about trees for a few minutes. So, yes. So let's let K1 prime be the minimum over all UV in the edge set of H with weight 0 of UV equal to K0 being the minimum value of weight 1 of UV. What we are able to show is that for any graph H, triangle free or not, and n at least the order of H, the number of vertices in it, the average degree of an H-saturated graph cannot be much less than K0 plus K1 prime minus K0 divided by K1 prime plus 1, n over 2 minus C. And if K1 is bigger than K0, so if we're not in the case with the chair, then we can push this up a little bit bigger. The saturation number is bigger than or equal to K0 plus K1 prime minus K0 over K1 prime, just like in that warm-up bound that I just showed. So you might ask if this is the one that looks like the warm-up, what does this one look like? Essentially what this one, the top one looks like is if if the high degree vertices don't need to have high degree neighbors. So for this one, we just have high degree vertices kind of making stars to our low degree vertices. And so that's why the denominator is one larger for that one. Okay, now let's go back to our chair one more time. So like I say, this edge right here is our important one. It minimizes, it's the only one that minimizes weight 0. So this is where K0 is coming from. And let's look at our graph obtained by taking vertices of degree 1 and vertices of degree 3. Well, what does that look like? It looks like a disjoint union of stars, right? And now, when I add my edge in, indeed, I have this edge playing the role of this one. I have this edge going towards a high degree vertex, except I have a problem. My high degree vertex isn't high enough to actually find a copy of H. And that's because H is triangle free, whereas one of the edges contributing to the degree of this high degree vertex in the star makes a triangle. Okay, so the final lower bound that works well for the chair and for trees is that we can actually push up the degree of a high degree vertex by 1. So in fact, stars on 4 degree 4 vertices with leaves, they are the minimum saturated graphs for the chair. And this agrees with a general lower bound we have. So H triangle free and K1 prime being at least K0 plus 2, which just barely works in the case of the chair. We do need, for this theorem to go through, for the more general one, we need for the K1 prime to be more than one more than K0. We have, we can basically add 1 to the high degree vertices. Plus 1 minus K0 over K1 prime plus 2, and over 2 minus C. And if K1 is bigger than K0, then sat and H. Oh no, this one should have been a plus 3. And now K0 plus K1 prime plus 1 minus K0 over. No, I was right. I was right with the plus 2. Sorry, disregard my K1 prime plus 1. Okay, all of this is a lot of formulas, so let's look at a tree like I promised. What I'm excited about with this theorem is its effectiveness on double stars. So a double star is a tree that looks like this. Sorry. We're going to have 2 central vertices of degree S and T respectively. These are degree. So S minus 1 leaves extending from one of its centers, and T minus 1 extending from the other center. And so in 2009, Fodry, Gould, and Jacobson studied saturation numbers of trees, and they showed that, so SST is the notation I'm going to use. They showed that S2T has the highest saturation number out of any tree with respect to its, sorry, the lowest saturation number out of any tree. I got that all backwards. And this is a kind of a special thing. They got bounds for arbitrary double stars, and they got the asymptotics right when S is equal to T. And in fact, in that case, the asymptotics agree with our kind of trivial K0 lower bound. Now, for S not equal to T, then we get, so the weight functions for this edge here are S minus 1 for K0 and T for K1 prime. And so our lower bound is on average degree is S minus 1 plus T plus 1 minus S minus 1, so that's T minus S plus 2, divided by T plus 2. And this is the correct answer, because it agrees with our upper bound construction. The upper bound construction says let's put vertices of high degree to vertices of low degree. And here's a pretty simple way to match them all up. If you make 2 copies of the high degree vertices, then you can put a bipartite graph between these 2 sets of low degree vertices, which are the same cardinality, so there's an even number of them. and you can get a graph which has exactly this average degree. And so simplifying things a little bit, we see that the saturation number of SST when S is not equal to, when S is strictly less than T, is about S times T plus 1 divided by T plus 2, N over 2 plus O of 1. This is kind of nice. Fodry, Golden, Jacobson determined S as a lower bound and S plus 1 as an upper bound. And it's kind of cute, I think, that it sits right in between with this S minus 1 is a lower bound and S is an upper bound. And it's just that little bit underneath S. And I will probably conclude my talk there before I keep talking about other trees and spend too much time. So let me go back to my thank you slide. Thank you, everybody, for listening. And here are some references if you'd like them.
Let's thank the
Thank
speaker.
you. Thank you.
And we'll take questions after I stop the recording. Just give me a moment. Where did the button go? There it is. Yeah. Thank you.